Telescopes allow us to perceive very faint light that has traveled to us from great distances, light that is so much fainter than our unaided eyes could ever see. And although telescopes come in many designs, they all have some basic features in common: a light collector, the lens or mirror that gathers the incoming light, and a light detector to produce an image from the collected light. Even the most sophisticated telescopes, like the Hubble Space Telescope, are designed around these same components: a primary mirror to collect light and focus the light onto the electronic detectors that are the telescope's eyes. In fact, not only can modern telescopes detect far fainter light than our eyes, they can also detect wavelengths of light beyond what our human eyes can see.
The telescopes that are much better than our eyes, they're collecting this electromagnetic wave at basically different wavelengths. And then by analyzing, by interpreting the data that we are collecting at this different wavelength, we are building this picture of the source.
Telescopes are designed to collect light beyond visible wavelengths. Longer wavelengths, like infrared, microwaves, and radio waves, or shorter wavelengths, like ultraviolet, X-rays, and gamma rays. The wavelength of light collected dictates the telescope design. Radio waves are very long, so a typical radio telescope has a large dish to allow it to collect enough radio waves to produce an image. And because X-rays can pass right through most mirrors, the Chandra Space Telescope is designed with a series of nested mirrors that gently nudge the very energetic X-rays onto its detector. By looking at different wavelengths of light, a different view is revealed, leading to a better understanding of our universe. It is like the imaging tools used in hospitals, where healthcare professionals observe their patients using different parts of the electromagnetic spectrum. Each technique yields new information about the patient. The same holds true for the objects that make up our universe. To our eyes, the sun is a blinding sphere, but by filtering its light and looking in specific wavelengths, we can see many of the structures below its bright corona. Nebulas are beautiful but opaque in visible wavelengths. Yet in infrared wavelengths, we can see through the interstellar dust to stars being born inside.
By looking at different examples of signals at different parts of the sky with different time scale, you build a model, and that's what theorists do. And then they examine it by looking at more data, and they refine it and they refine it until we understand.
CHIME is a new design of a radio telescope that is helping astrophysicists solve one of astronomy's most curious mysteries. Fast radio bursts are very short and intense bursts of radio waves that are so energetic they can release as much energy in a millisecond as our sun does over a few days.
Fast radio bursts are energetic, millisecond duration bursts of energy. They basically fall in the radio domain of the electromagnetic spectrum.
But as mysterious as they are, radio telescopes like CHIME have revealed that they are much more common than we thought. A traditional radio telescope is designed to look at one patch of the sky in great detail, but the CHIME telescope scans the entire sky each day, detecting far more fast radio bursts in the process. The sheer quantity of observations by CHIME may provide astrophysicists with the data they will need to solve the mystery.
As more data becomes available, it's easier for people like me to build a model, and an experiment like CHIME is helping us to understand.
In the Atacama Desert in Chile, astrophysicists are observing the universe with microwaves. Microwaves are easily obscured by water vapor in the atmosphere, but the high altitude and dry conditions here make detailed observations possible.
And so one of the experiments that I'm involved with is the Atacama Cosmology Telescope. So it's a telescope that collects microwave light on the top of a mountain in the Atacama Desert in Chile.
It has been known for decades that the sky is filled with microwaves that have been traveling through the universe since not long after the Big Bang.
The light that you're seeing is coming from a really early period of the time. The universe expanded since then, and so it's been stretched out to the microwave spectrum. The first thing you see when you make a map of the microwave sky is what looks essentially like noise, right? I mean, it looks like lots of blobs of cold spots and hot spots. But it's first of all important to realize that those hot spots and cold spots are really tiny fluctuations. And then you realize, oh, it's those tiny fluctuations that eventually became the structure. Like they formed stars and galaxies and clusters eventually.
Each time this ancient light interacted with cosmological structures in the universe, it created a signal that is preserved in the tiny fluctuations of the microwave background.
What you're essentially seeing is the gravitational influence of all the matter in the universe, and what that helps you do is map out all of the structure in the universe.
It is amazing that the telescopes we design and build on and around our small planet can gather the light that has traveled to us from such great distances.
I 100% would say this is one of the most exciting things you can do if you're interested in physics, if you're interested in the big questions, the most fundamental questions that humans can ask.
Astrophysics is beautiful. You look at it, it's beautiful. And when you try to understand it, you see the beauty. And yes, they are far away, but they are giving us what we need, and that's their light.